Have you ever questioned why space remains shrouded in darkness despite the abundant presence of stars and galaxies? In this presentation, we will meticulously explore the various reasons that explain the apparent darkness of space, from the absence of an atmosphere to the influence of dark matter. Delve into understanding how the nature of light and the universe's continuous expansion impact the trajectory of light in space, and gain insights into cosmic background radiation as well as current knowledge about enigmatic dark matter. This content is especially recommended for those wishing to expand their knowledge of the universe and unravel the fascinating reasons that make space an apparently shadowy domain. Join us on this cosmic journey and explore the wonders of the cosmos. The absence of a significant atmosphere in space plays a fundamental role in creating cosmic darkness. Unlike Earth, which has an atmosphere composed of gases and particles, intergalactic space is largely a vacuum. Earth's atmosphere acts as a scattering medium for light, spreading sunlight that reaches Earth and illuminating our planet. In space, the lack of this scattering medium prevents the creation of a day or night sky similar to Earth. In other words, there is no solid surface or atmosphere in many regions of space to reflect the light from a central source, such as the Sun. This results in vast dark areas between stars and galaxies, where light is not reflected or dispersed significantly. The darkness in space becomes evident when we look at the cosmos beyond our own galaxy. Light from distant stars and galaxies has to travel great distances to reach Earth. During this journey, it faces little or no atmospheric scattering, meaning there is no diffuse glow that makes space visibly illuminated. Although the Sun is an intense source of light for Earth, its influence does not extend indefinitely through space, and many regions remain immersed in darkness. Thus, the absence of an atmosphere to scatter light substantially contributes to the generally dark appearance of interstellar space, an intriguing feature that instigates exploration and a deeper understanding of the mysteries of the universe. The low density of matter in vast interstellar expanses contributes to the apparent darkness of space. Unlike densely populated regions of a galaxy, where stars are clustered, many parts of interstellar space lack significant celestial bodies and matter. In these vast regions, the amount of matter is so minuscule that there are no substantial sources of light. While in our own solar system, the Sun's light illuminates planets, asteroids, and other objects, in many parts of space, the scarcity of luminous bodies contributes to a notably darker environment. Additionally, light emitted by distant stars can encounter obstacles on its way to Earth. Dust and gas scattered through space can absorb some of this light, further reducing the luminous intensity reaching observers on Earth. This interstellar absorption phenomenon contributes to the dark areas between stars and galaxies, creating vast stretches of cosmic darkness. Therefore, the combination of low matter density and interstellar absorption causes substantial areas of space to remain in shadows, contributing to the overall perception of darkness in the cosmos. It is an intriguing demonstration of how the uneven distribution of matter in the universe influences the amount of light available to illuminate interstellar space. The continuous expansion of the universe is a fundamental dynamic that intriguingly plays a role in contributing to the apparent darkness of space. As we move away from our vantage point, whether on Earth or any other point in the universe, we can observe that galaxies around us are moving away from each other. This phenomenon results from the fabric of space-time itself expanding, a discovery dating back to the pioneering work of Edwin Hubble. As galaxies move away, the light emitted by them is subjected to an effect known as redshift. This shift happens because the wavelength of light is stretched as the space between the luminous source, the galaxy, and the observer, such as us on Earth, expands. Redshift is particularly relevant to the issue of cosmic darkness. Light that originally might have fallen into the visible spectrum, like white light, can be stretched to longer wavelengths, often surpassing the visible region of the electromagnetic spectrum. As a result, redshifted light may extend beyond the perceptible range for our eyes. This transformation in the color of light can make distant galaxies visually more challenging to detect, contributing to the generally dark appearance of interstellar space. Although galaxies still emit light, this redshifted light may not be detected by our eyes without the aid of specific instruments capable of capturing longer wavelengths. Therefore, the expansion of the universe, with its redshift effect, adds a fascinating layer to the understanding of cosmic darkness, highlighting how the dynamic features of space-time influence the visual perception of the universe that surrounds us. Limited light emission by stars is crucial in explaining the apparent darkness of interstellar space. Even the brightest stars visible from Earth have their light significantly attenuated as it travels through the vast interstellar space. Factors like light scattering by interstellar particles, absorption by dust and gas clouds, and the nature of light propagation in space contribute to this attenuation. The amount of light reaching Earth from distant stars can be so reduced that it becomes challenging to perceive with the naked eye. This is particularly evident when observing stars in distant galaxies, where light can travel enormous distances before reaching our planet. The gradual weakening of light over this journey results in a luminous intensity that often falls below the threshold of human visual detection. To overcome this limitation, astronomers use advanced optical instruments such as space and ground-based telescopes equipped with sensitive sensors. These instruments enable the capture of faint light, revealing details and information about distant stars that would otherwise be imperceptible to the naked eye. Thus, the limited emission of light by stars in the vast interstellar space highlights the importance of sophisticated technological devices for the exploration and deeper understanding of the cosmos. These instruments allow scientists to unveil the beauty and complexity of the universe, even when the light emitted by stars faces considerable challenges during its interstellar journey. Understanding cosmic darkness is deepened when considering two intriguing elements: cosmic background radiation and the enigmatic presence of dark matter. Cosmic background radiation is an emission of energy that pervades the entire universe and is a trace of the early cosmos, originating approximately 380,000 years after the Big Bang. This radiation is mainly composed of photons, light particles, that propagate through space, filling interstellar regions. Despite being a form of energy, cosmic background radiation is predominantly in the microwave spectrum, making it invisible to the human eye. This radiation contributes to the dark background of space, constituting a background light that permeates every corner of the universe. Although not visually perceived, its presence is detected and studied by astronomers using sensitive instruments such as radio telescopes. Cosmic background radiation provides valuable information about the initial conditions of the universe and its evolution over time. Dark matter is another crucial piece in the puzzle of cosmic darkness. Unlike normal matter that makes up stars, planets, and everything we can directly observe, dark matter does not emit, absorb, or reflect visible light. It interacts with conventional matter in subtle ways through gravity, being detected indirectly by the gravitational effects it exerts on visible matter. The abundant presence of dark matter in the galaxy and the universe contributes to the apparent darkness of interstellar space. While it does not emit light, its gravitational influence affects the distribution of visible matter and shapes the formation of cosmic structures on scales much larger than those directly observable. In summary, cosmic darkness reveals itself as a complex enigma, the result of the intricate interaction between various astronomical phenomena. From the lack of an atmosphere to the presence of dark matter, each element contributes to the apparent darkness of interstellar space. This journey of understanding leads us to contemplate the vastness of the universe in a deeper and more intriguing way. As we delve into the mysteries of the cosmos, we are challenged to expand our horizons and explore beyond the limits of current knowledge. The darkness of space, far from being an obstacle, is an invitation to scientific innovation and the continuous quest for answers. Therefore, let this exploration of the elements that make space an apparently dark expanse serve as inspiration. I invite everyone to continue the pursuit of understanding the universe, whether through scientific research, education, or simply the appreciation of cosmic wonders. In each discovery, we are closer to unraveling the secrets that permeate cosmic darkness, offering a more enlightened view of the complexity and beauty of the cosmos. After all, darkness, far from being an end, is the beginning of a fascinating journey toward the stars. Now, if you want to explore some fascinating unknown destinations, check out the video playing on your screen. See you next time.